Everyone. So today we have a special session of the seminar to receive our invitee. Today Professor Francisco Correa is visiting us from the Universidad Austral de Chile, and he's going to talk about integrable system, gravity, and field theory.
So thank you very much. Thank you very much to everyone, and especially thanks to Claudio for the nice invitation. So today I'm going to talk about some related work regarding integrability, field theories, which includes also gravity. And these works are done in collaboration with Marcela Cárdenas, Cristian Lara, Miguel Pino from Universidad de Chile, and also in collaboration with Fring from University London, Taira, which is now in Patano Lab in Japan, and Julia Sen, which is in Los Alamos, United States. So at the beginning, I would like to give you a kind of flash introduction to integrable models and their relation somehow with physics, but also with field theories and gravity. So I would like to give you a small trip about how these things are related and how we are interested in that. And then I'm going to talk about a bit of non-Hermitian physics, just to give you a taste of what is nice and important about this area, but also related with our related written research. And then I'm going to tell you about a nice problem regarding space-time dynamics and integral systems. And at the end, also, I will talk about some soliton models related to field theory and some insight regarding non-Hermitian physics and also linear stability. I know here there are a lot of people which are very, they know a lot about the stability. This is a very simple way for you to study stability, just linear stability. But I will try to convince you why we are interested in also the big instability, just linear, just to understand some physics properties about some solitons that we were studying. So the fields that relate to integrability and gravity have been studied from long time ago. Actually, since the beginning of the study of the inverse scattering method, these techniques were applied very quickly to study the Einstein-Maxwell equations, which unify very nicely the gravity and electromagnetism. And in this way, many kind of solutions, very important to physics, were studied from cosmological models, collision of gravitational waves, which also, this is a nice book regarding this area, which includes a lot of results. So that here, the amount of literature is huge. I cannot tell you about all the reference, but with these techniques, one of the most important solutions in black hole physics, like the Churchy black hole solution or Kerr black hole, can be obtained from this result. But also there are another kind of result, the Taunat solution, the Limax-Tosatu solution. There are a lot of solutions which are quite important and interesting from the gravity point of view, which can be obtained and understood from the gravity side, from the integrability side. So there are a lot of literature around. These are also nice books which also relate all the powerful techniques of integrability to gravity. So this is one kind of example that connects integrability with field theories, but this is not the only one. One other nice example is the Grosvenor model, which is a very simple model which describes the self-interacting fermions. Actually, this is one of the workhorses with model when you study quantum chromodynamics. And here is the serial housing, which is the Namu-Jonassini model. So these models were very important in order to study several features of quantum chromodynamics, like asymptotic freedom, dynamical mass relaxation. When as you know, when there is some kind of symmetry breaking, this is very important for physics, the tidal symmetry breaking also studies. There is still open problems regarding the phase diagram, and these models, in 1+1 dimension, they were well studied, and they were proved to be very interested, and you can actually solve the problem because some relations with integral systems. And actually, one of the nice relations is that in order to solve this problem, you somehow solving the gap equation, you can transform this problem to a kind of beta type of problem, stationary problem. Actually,
excuse me, in the sidebar is complex conjugate and with a beta type, or it's just complex?
Yeah, well, it depends. Yeah, could be complex conjugate. Yes, yeah, could be. But actually, this is our premium, so sometimes you need to include some additional additional constraint with some gamma matrices. Yes, it depends on how many dimensions this will be kind of different. Yes, but include something else. They will include something else. Yes, but in principle, yes, there are these that includes the complex conjugate. So this is actually please, if you have any questions, just interrupt me. I will be very happy if you have questions. This Hamiltonian is nothing else than probability of the Gens Hamiltonian, and I will not show the details, but I just want to tell you that solving this kind of problem, which is a completely field theory, these are just fermions. You construct some kind of composite bosonic kind of fields, and you can transform the problem to solve and find this spectrum of this system, which transforms somehow then to study just the diagonal representative operator, which is just kind of a particular case of the Green function, and this is very related with some nice hierarchy of integral system, which I will tell you later, and you can understand that these features with integral systems, and you are able to solve a lot of problems, understood a lot of solutions from this model, which are actually so far there are still open problems like that. So another good example of which connect field theories with integral system is regarding this Hamiltonian that probably you have seen before. That with this Hamiltonian you can construct the Poisson-Bracken structure, and finally it's like obtain the equation of motion, the KDD equation, which is a very nice equation. It's a nonlinear equation, so in principle it could be very complicated to solve, but it has a lot of features, and these features are related with integrability. So in this solution as well, this is also one of the most well-known systems regarding that display soliton solutions. The solitons have in the KDD have very nice properties. One of they always travel with different velocities. So you can create compounds of solutions that interact with each other. They scatter between them, among them, and they move asymptotically with different velocities. But also the very important and particular feature is that they don't change the shape after the collision. So this is a very nice feature of the solitons. So here you see how two solitons interact. The heap faster the speed. This is how this is going faster. And this is just the direction of those two solitons. And for instance, this is the interaction of three kind of soliton solutions. Of course, this is not the unique kind of solution. There are more types of solutions in this kind of system. And well, and this also show you this study of these kind of equations show you the nice relation between mathematics and physics, and this is also kind of the spirit of the talk that I will also mention about the self-interaction models like Gross-Neveu, that somehow you are solving one problem of, for instance, here the KDD solitons, and somehow you are solving another completely, in quotes, unrelated problem. And this is also something that, I think that all of us, mathematicians and physicists, we love to find such a connection. So here, for instance, it's very interesting that the interaction of the KDD solitons is very closely related with the isospectrality problem in quantum mechanics. And this is because of the inverse scattering method. So I will just to give you a little bit of the taste of this, what I mean with this relation, and this. So the spectrality and the spectral design are very related in this case. I will show you what I mean. So, for instance, you can return to the question of Cárdenas. So, if you pose the question, if we have a drum and we produce a sound, can we hear what is the shape of this drum? So just with the sound, can we reconstruct what is this kind of the drum? Well, the question is already known, but let me just rephrase you this question in the quantum sense. So can we hear the engine values of potential? Can we display a two-Stungerville operator, Schrödinger operator, and we have kind of a different kind of spectra? Can we just reconstruct what is the potential and the Stungerville problem related with that? So this is something quite interesting. And for that, just let me remind you, you take the interaction about these solitons solutions, and now you may think or may consider these solutions like a potential in quantum mechanics. What I mean with that is just take a snapshot of this plot in one particular time, and this will be a certain kind of potential in quantum mechanics. Okay, I'm not saying that this potential is moving in time. Just take a snapshot of this potential and of this interaction, and this will be a potential in quantum mechanics. So all this, if you take a snapshot, all this kind of infinity number of potentials have the same features. So they display two bound states at this energy level. And actually, when they go here, they collide in the middle. This is nothing else than this kind of potential with the pure stellar potential, and so it's a very nice and interesting feature. So, in somehow understanding the collision of solitons, you are solving a very important problem in quantum mechanics, and this is why the inverse scattering method was so important. So, well, then you can pose the question: so, can we design the spectrum in quantum mechanics? Like that's the answer is yes. You can design the spectrum in quantum mechanics by many different ways. These people studied what is now like that Buchran transformation. This is a way to design the spectrum of quantum mechanics. I will not show you the details about that, but these also are very important for the construction of solitons. When you construct solitons and different kind of theories, there are many methods, like background transformation, Hirota method. There are many ways. This is just one of the methods that is almost present in all kind of soliton solutions. So, but these are what I want to emphasize, that these are very related with the design of quantum mechanics. Actually, what is known like supersymmetric quantum mechanics, just a toy model, just to study the supersymmetry breaking, but basically with this method and supersymmetric quantum mechanics, you can study a lot of potentials, a lot of systems in quantum mechanics, but it's nothing else than this Buchran transformation. So, for instance, when you have the typical example of supersymmetry breaking, you have two kind of supersymmetric models, thinking that they are almost the same. They have almost the same spectrum, but one of the energy is missing. This means that you have a supersymmetry breaking, and this is kind of almost the spectrality. Here you have exact supersymmetry, but the idea is that in this way, you can construct many types of systems. Just to tell you how this works, for instance, you may consider a potential in quantum mechanics like a free particle, no potential at all, and you have no bound state. And with this method, for instance, you can construct, with this machinery, you construct from starting with the solution from this, you construct a new system, like for instance, this one, which is very related with the KDB case. This potential well displays just one bound state, and on top of that, there is also very important, and this is also very related with the case on the inverse scattering method. The transmission here, the reflection coefficient, in this way, of the scattering states here is 0. So, despite the fact you have some non-trivial interaction, here you will have just pure transmission. So, and this is done with this kind of Darboux transformation or supersymmetric transformation. If you do it again, you can construct a new, another potential actually, and this is exactly what I showed you before. This also is a two soliton kind of potential display two power states, and this is also in reflection. And this is very nice that here I think some very particular triangle numbers that could be. So these are there are a lot of things that are interested from this point of view. So just tell you how somehow things are connected between quantum mechanics and solitons. It's quite nice. How we can understand all these features. So how these relations appears between one system and another. For this, I'm going to show you another example, another integral model, which is the non-linear Schrodinger equation. And I would like to describe you a few things about this equation, just to give you an idea of what I'm going to construct later. So, well, this equation is very important in physics. Actually, it's very related with the propagation of light in fiber optics. So the history of this equation and the relation with optics is quite interesting. But on top of that, there are a lot of other applications regarding some of those fields, but there are a lot of more. So actually, if you look at internet, there are a lot of applications of this equation. So what I would like to show you is how we can obtain, or what is the origin of this equation. For this, I would like to retrace to the Lax permanence, which is about, imagine you have two linear problems. Here you have a field side, here the derivative in time, or the parameter t, in the derivative in x, and here you have a linear problem with some object u and b. Okay? Then, well, you may consider what is the compatibility condition of this equation in the sense of here you derive in terms of x, here you derive in terms of t, and this gives you some compatibility conditions. It turns out that this kind of equation, and in particular many of the integral models, can be written in this form, the Lax permanence. And in particular, this is nothing else but the zero curvature permanence. So actually, when you perform the compatibility condition, the equation that appears of this kind of style for the u and b objects. Here is the commutator, and this is the zero curvature permanence. These things are very related and practically the same. And when you see this kind of equation, of course, you think, well, at least from the physics point of view, you remember something related with gauge field. And this is also very important for what I'm going to show you next. So what's the idea here? If you find some object u and b, and you can construct in such a way, you are very near to have an integrable system. So for instance, if you consider here u in this way, where two arbitrary functions q and r, here there is a lambda, this is nothing else than the spectral parameter. And then you may consider if this here is just a 2 by 2 matrix, and then you may consider what is the kind of other object b that will transform this kind of equation into the nonlinear Schrodinger equation. This is what we want to do. So for this, after some calculation, we realize that you may consider that the matrix takes this form. And when you're solving this, and this is just an example, here you have like a derivative, here you have some kind of the matrix, and this is very related to solve a quantum relativistic problem. And actually, this is the way how quantum mechanics appear in this model. So when you solve this linear equation, it somehow appear some kind of quantum problem. Here, this is very related with the Bogolinos problem that I showed you before. So you are solving something another way. So you may consider also this lambda, which is the vector parameter, is related with some energies. Solving this Lax permanence and the zero curvature permanence, you are solving, in other words, some kind of related quantum problem. This is how the relation appears. So then the choice of how to find what are the A, B, and C is in principle is not simple in the genetic case, but there are also recipes and ideas to how to expand this, and may you consider like an expansion in terms of the spectral parameter. And if you work a bit on that, you realize that if you find the functions A, B, and C in this form. Here, there is some just a constant alpha. It is possible to relate with the KDV equation. So I will show you how. So you just need to put this equation that goes to this equation into the B and just perform the zero-Coulomb formula. So as I said before, when you find these objects U and B, it's kind of equivalent to say that you are finding some integral system. So actually, most of the integral systems are, well, as I know, all the integral systems I know, they have this zero-Coulomb formula and the Laxberg formulation. So when you plug in this equation into this one, then it's a 2x2 matrix, but actually this will transform into two equations, one for the dynamics in Q and one for the dynamics on R. And these are, of course, complex equations. Okay? And then it came out the question, so can we transform these two equations into just one? And this is how you may think that R is just kappa, it's a constant times Q conjugate. And when you plug into this equation, you will find that these two equations transform into this one, which is nothing else that is non-linear Schrödinger equation. And of course, it's a kind of Schrödinger kind of problem. Here, first derivative times an imaginary unit, two derivatives in Q. But here now, like the potential in both is related with the same field, the complex one. So this is how the non-linear Schrödinger equation appears. But actually, all this scheme that I am showing you before is not just related with the non-linear Schrödinger equation. All this scheme is related with the lowest cup in the well-Segur AKNS hierarchy, which includes, as a particular case, Sine-Gordon, KDV, MTDV, non-linear Schrödinger Pirota. So many, and a lot of more. So many of the most well-known integral systems are somehow encoded in this structure. So I will go back to the AKNS equation in a minute. So, well, so far this kind of was a kind of flash or introduction to integrability, just to give you a taste of how this works. But everything what I say so far is a very well-known fact. This is very well-known. It's very well studied. You may find a lot of literature around. So, but the question still is, can we find new phenomena in physics, but also some interesting facts in mathematics? And this is what I'm going to show you now. And that's what I will introduce the concept of pretty symmetry. The journal Nature in 2015 showed that one of the top 10 physics discoveries in the last year was related with the discovery of the parity symmetry breaking in optics. So this is kind of a symmetry which was found in nature with some kind of optical models, and also the breaking of this pretty symmetry. And this is very related to what I also did with my recent research. And what is pretty symmetry? Well, P stands for the parity inversion, which is quite important in physics, but also the P is related with the time reversal symmetry, which somehow conjugates the imaginary units. Okay. So what is the point in somehow of this, or why this symmetry becomes interesting and important? Because you may have quantum complex Hamiltonian that might display real eigenvalues, and this is what was quite shocking somehow, in the sense of usually you know that you have a Schrödinger equation or similarly problem. You require that the equation and the Hamiltonian must be Hermitian in order to have real eigenvalues, and you can prove that this way. But actually, this is not the only way. And actually, this goes back to Wigner in the 60s, which showed that if you have an antilinear symmetry, well, I just mean that we have the same property of a linear operator, but now you just conjugate a constant. Okay, this is that when you go through a function or a constant, just conjugate. When you have this kind of operator in quantum mechanics, you may have a real eigenvalue. So the observation came from Wigner. This is very important to see. And just I would like to show you that when you have a kind of eigenvalue equation, and you have a symmetry of the corresponding Hamiltonian of something that commutes in the case of PT, but also simultaneously the wave functions of the solution of the eigenvalue equation, but also wave function of the PD symmetry operator. You may find that all the eigenvalues are real. So just let me rewrite this equation in this way, and now let me use the fact that the wave functions are solutions of are also eigenvectors of PT, and now we will use the fact that this operator just commutes. Now we use again the eigenvalue equation, and now we will use the fact of having an interlinear symmetry. So now we will pass through the energy to this operator, of course this conjugate, and now we use again this relation, and then we obtain this. So in just one line, you can see that having these three facts, you can show that in this case you ensure that you have real eigenvalues. Okay. Well, this was like the beginning of the idea to consider the effective symmetry. Actually, Bender and Boston in '98, they studied this very simple Hamiltonian, which was inspired in somehow with like an harmonic oscillator, but now you have something which is quite complex. Just I and X cubed, but clearly this is PT invariant because you have here an odd function and here I. So PT is clearly a symmetry of this operator, and they understood how, in this case, what are the possibilities to have a real spectrum. Well, this was just the beginning in this area. Then a lot of people that have been working on this problem now. Actually, there are kind of books of many people also working on this field, is transforming their own area of research. But many years ago now, there appears, well, not so many, but 2017 and now 2009, they observed this kind of symmetry in objects. So I'm not going to explain all the details, but yes?
Just a question. If you have PT symmetry, spectrum is obliged to be real, or it's just that if E is in the spectrum, then E star is also in the spectrum?
Yes. Well, it depends kind of PT symmetry, but you need an extra condition. So you may have this PT symmetry which commute to the Hamiltonian, which this is what we call symmetry. But then you require that the wave functions also eigenfunctions of the PT operator, and this is crucial. And this sometimes happens, sometimes not, and sometimes this actual symmetry breaks. And this is what appears PT symmetry breaking. So yes, this is the idea. Do you have another question? Good. So, well, the interesting fact was that somehow these quantum systems are related to optical systems. So in this context, what people understood that appears this parity symmetry breaking. So we don't claim that there is a real physical meaning of a complex potential in the sense of Schrödinger equation, but all the machinery on the theory here can be applied to an optical context, where the potential here will play a role of the refraction index in optics. This is why it could be complex. So in this scenario, a lot of experimental observation appears. Now actually there are a lot of these books also that explore the different possibilities of have this parity symmetry in different kind of applications, graphene, topological insulator, acoustical system, optics. So they are now everywhere. So actually, well, non-Hermitian, and this is what we call non-Hermitian physics, because we allow to the models to lack the Hermitian properties. Now, there are a lot of field theory that have been studied here. There is a kind of, a list of some people working in this area. They have been working in very important mechanisms like field mechanics or Boltzmann theory. In field theories in physics, they study monopoles, BPS theory, Schirmer models, all related with this kind of symmetry. So the punchline is that you may find now complex kind of field theories that have real eigenvalues, real energy, this real energy are related with some symmetry, and this is how you obtain these relations. One of the nice models is the BDS CMM model, which is a nonlinear signal model, and it's very nice because this model has exact analytical solution of topological solitons. But this is nice. It's a nice model because this was studied and inspired to describe the bind energies independent of the value number. So just to describe, let me in a few words to describe the nucleus. These models also display very nice features and also solve kind of problem of some another nonlinear sigma models. So just to let you know that you may find in these fields, in this BDS schema model, some complex fields. This is, for instance, just like kind of the real part of a complex field that will have real energy. And this is something quite interesting. So you may also find this kind of system that you may think that they are not physical in the sense of have some complex nature or not Hermitian, but at the end they have real energies and real conserved quantities. And this is something which is now being explored in a lot of field theory. Well, what about integrability? Well, I will just remember something that I was given a seminar in 2015 related to the KDD equation. With the KDD equation, if you look, it's clearly invariant under PT symmetry, and you now may allow to the KDD equation that, of course, the KDD includes the fields are real, but you may allow to the complex to be complex, to the fields to be complex. So they have a real and imaginary part. But this allows, this is just the idea of this relaxing this condition, this allows to find new kind of KDD solitons with different behavior. So, and what I'm going to show you here is just like the real part of a KDD interaction. I will not show the imaginary part, but it's quite similar. And these solitons behave in this way. So this goes like a train of solitons, but they have non-trivial interaction. So they interact in some way. They just not travel like a train of solitons. They interact in some way. And this is quite different than the solitons, the usual soliton, because the usual solitons, as I said before, they travel asymptotically with different velocities. So these kind of solitons are quite different. These are very close solitons related with the roadways. You see the amplitude, they really go very high when they interact. So this is a very nice soliton, and these solitons are obtained by making the field allowing to be complex. And of course, you may find another kind of very nice interaction of complex solids. So, but what is important here also? So you may think, oh, now, well, okay, you have some KDD equation with complex field, but what about the energy? What about the conserved quantities? So this KDD is an integral model. This means that this model may have infinity amount of conserved quantities, but you may prove that with the PT symmetry plus integrability of these two properties ensure the reality of all conserved quantities. And this is, so for us was quite surprised. So you have infinite amount of integrals, which here U is complex. So you may think now, well, now these numbers are going to be some complex, but no, because all the imaginary parts goes to zero. So, and this is just because of this PT symmetry. So this is something like for us was quite exciting to start to learn more properties of PT symmetry in the KDD equation. Okay. Well, this is not just the only case. We also work with a modification of with the nonlinear Schrödinger kind of system. You may include an next term from the hierarchy, and inspired now on Ablovic and Muslimani. They also explore the possibility to have nonlinear, non-local solitons. This just means to now R intends to just be a conjugate. Now could be kind of could be with a minus x. This is what we call non-local, and these two under this condition, these two equations also transform into one. So this is why they become very interesting here. And in this kind of And this kind of system, this is work that we studied together with Julia and Andreas. We find new kind of solitons, different kind of behaviors, but also with all the real conservatives, all the conserved quantities are real. But also we also study different kind of system related by gauge transformation of this, like the extended lambda with the equation. There is a non-local version of this. So all these properties inspired by PT symmetry, because this is kind of very the parity here is present. This also inspired to find new integral models. So this is what I want to say, that this PT symmetry also allows to find new kind of systems. And well, of course, this is not the only case. You now may produce different kind of PT symmetry inspired new integral models that all these two equations will reduce the same, time levels, that PT symmetry, and so on and so far. So there is a lot that you can study around this equation. Yes.
If you recall again all the symmetries that you can choose is success. None of them is like a charge symmetry.
What do you mean with charge symmetry?
Well, that's a question. If you remember, please.
Yes, yes, I understand now. And yes.
If you, because this, I don't know how to say this because I know that it's something physical, but
yes, yes.
I don't understand the mathematics. So for me, I know that essentially, I think that you assume that no physical system violates the CPT, right? So my question is, well, in this physical system, what is the CC?
Yeah, no, that's a good question. So first of all, you have to go to the field theory. I didn't show what is the field theory behind, but in this particular kind of system, there is a nice property that sometimes, and this is in order to solve in order to answer your question, it's true that the CPT, you have instead of PT symmetry, when you have field theory, you have a CPT symmetry. But sometimes the CPT symmetry is not a symmetry of the system itself. So I agree with you. But this transforms to another system, which is very related with this, and then you can show that this transformation map ensures the reality of the energy. So it's a symmetry here in the field theory sometimes work in another way. So instead of just saying, so if in field theory you relax more the question of having a real symmetry. I didn't talk about that just to give us some more details, but instead of having a symmetry of the system itself, you have a symmetry between two systems. And this symmetry between these two systems, you can check that you can allow to have the real conserved quantity. So sometimes the charge symmetry could be not present, and we transform into a new system, but then you can work it out that the two systems together ensure you the reality of energy. So it works in different ways. And this is because in field theories are kind of more tricky, and this is of course not quantum. Good. So there are more applications in physics. Well, just now let me tell you about some related with the system related with the AKNS hierarchy. So as I show you, this hierarchy has the base of the zero curvature formalism in this way, but this is very related with three-dimensional gravity, and this is one of our recent results together with my colleagues from USAC. So this is the field equation of the Einstein equation plus negative cosmological term, is the negative cosmological constant. It is well known that these equations can be formulated as two copies of two independent Chern-Simons fields. Okay, so basically, what's the idea? You have some gauge fields, and you may transform this kind of field equations into two copies of a gauge field equation, which is nothing else than a zero curvature quantity. This cannot be done always. You may create this idea specifying some particular boundary conditions of the gravitational field. The boundary conditions are, as you may know in mathematics, in quantum mechanics, integrability problems, but also here in gravity, what is the boundary condition is very important in gravity. This will tell you how asymptotically goes the physical system, and will define what is the background of the theory. But here, of course, as you have negative cosmological constant, your solutions will be asymptotically ADS until the zeta. But for instance, if this term is not present, then you have asymptotically flat on Minkowski. So, but this is very important and related with the symmetries and the boundary conditions. So this is what,
Excuse me,
yes.
the symmetry, three-dimensional means
2 plus 1. 2 plus 1. Yes. 2 plus 1. So, Correa and Andriel, they show that if you choose these boundary conditions of this gauge field in this particular way, in terms of some operators created with some symmetry with the SL2R generators, and you construct the gauge fields in such a way, so just apart depending on the angle and T, the dependency on R, which is like the radial coordinate, is just here. You can show that you can rewrite these fields in this way. These L0, L1, and L minus 1 are matrices of SL2R. They satisfy the diagram I showed you before. And look at here, if you recognize this term, you can construct actually in this way and choose this function to be in this way. And these are nothing else what I showed you before. These are the U and V. So the 0 to pure vector. Here, I didn't say, but here there should be the 2 copies. I'm just choosing just one just to show the detail. But if you you put a plus minus sign everywhere, this will apply for the 2 copies. But in this way, you may construct amount of gravity gravity fields that will have as a field equations nothing else than something related with the zero Fourier performance. In other words, you take the zero Fourier performance and you transform into so the zero Fourier performance you transform into the field equation that change sum of field. And with this observation, we found a lot of possibilities to describe gravitational fields. Indeed, the metrics have this kind of form. So here's the x goes to 1 and 2. So this is the 2-dimensional. This is the plus 1. And here the symptotic symmetry, and this is quite for us that was quite important, quite nice, that the symptotical symmetries of the gravity field are very related with the finite amount of AKNS charge. So this is not just a coincidence. I mean, this is not just, oh, you can transform the equations and looks nice, okay? So, but there is something more, that the physical properties of the conserved charges from the gravitational point of view are very related with the AKNS charge. And well, there are a lot of solutions in three-dimensional gravity that can be studied in this way. This is nice in the sense that we have developed kind of dictionary. So we found that the AKNS system that they slide, they code a lot of integrable system. The AKNS hierarchy is related with the ADS3 gravity because of this connection with the zero Fourier performance, but not just that. They are related because of the conserved quantity. So there is a lot of things to study here. Of course, we were not the same that study this kind of approach in the relating integrability and this kind of three-dimensional system. There are, I have not time to explain what other people did before, but there are references in our work. However, the value of what we have done in this sense is that very generic. It's for the AKNS that have a lot of kind of systems inside. So actually, there are a lot of questions in the point of view of gravity. I just wrote a list of what is interesting. So, for instance, what is the meaning of the scattering of the solution point of view of gravity? We don't know yet. What is the flat limit? With the flat limit, I mean with the cosmological constant goes to 0. Are these related with this structure? We don't know. So we know that, and I know the people here in the audience have to know that there are connections, as I showed you in the first slide, about Einstein-Maxwell equation in 3+1, the non-cosmological constant with integrability. But here we find something different with negative cosmological constant, and this is quite non-trivial. So what is the idea of this? So there is a kind of conformal symmetry, and also from the, if this gives us an insight of the ADS-CFT conjecture, and this is quite interesting because all the examples, the most successful examples in turn related with this conjecture are exactly related with three-dimensional gravity with negative cosmological constant. So should be something here. Of course, we have some quantum linear problems, as I showed you before, related with the integrability, and then related with the black hole entropy, and so on so far. There are a lot of questions that can be studied from this point of view. So just to go to the last part, I want to show you how all these kind of features regarding field theories and this new approach with field symmetry, we study some from some point of view of linear stability. I know that, as I said before, you people here knows a lot about stability. This is just a very simple approach, but I'm going to show you why perhaps was interested. For the ones that not know about linear stability, you have a Lagrangian density in 1+1 dimension, and you write the Lagrange equation. These are the ways, and then you introduce a small perturbation. So you take a static solution and you perturb with a small parameter. This is epsilon and the field chi. You can check if you put this these new fields into this equation. Appear this term that, well, this will be exactly 0 because of the solution is static, and the first order in epsilon, you will get this kind of equation, and this equation is nothing else like a Schrödinger type of problem. If you introduce this ansatz of the field chi goes in this way with exponential, like in the Fourier kind of expansion of the time exponentially by in time. This will transform this equation to a Stonelever problem, a Schrödinger equation, when the potential is just the second derivative of the potential here. But when you replace with the static solution, so finally this will be a potential in terms of x. Okay, this is what I want to say. This is quite well known in some very well known examples. For instance, if you take the Sine-Gordon equation, this is the potential that comes from the field theory. You take this is static king, and you may guess what is the potential. Well, the potential that appears here is actually the one that I showed you before. It's the one soliton reflection of potential. If you go to another field theory, which is not integrable like P to the 4, this is a static king, just this tangent, and in this case, this is quite interesting, it's the two soliton, the potential that appears is the two soliton reflection of potential. So this is actually very well known. If you are interested in the, well, actually this is exactly the ones that I showed you at the beginning of the talk. For the ones that are interested of these ideas in the point of view of classical and quantum field theory, I recommend this nice review by Jackie. It's quite, these two examples that I show you appear here, and some more features. So I think it's quite interesting to show. Well, what we studied was some solitons by the Bullock dot model, which is kind of extension of a Liouville kind of field theory. Actually, this allows to the thin theory. I will not tell you more details about the model, but it's just now you take this complex, this kind of fields, and we try to study the linear stability on this model. Okay. Now the idea is that the field equations and some of the solutions. This is one solution that this was already known that people, for instance, Taira, the study solution. This was not this is not, we didn't find these solutions, but these solutions with beta is real, they are singular. And of course, the conserved quantities they diverge because they have singularities here, okay? However, so we are not so complicated to make the fields complex. So when beta is imaginary, you can check that this is immediately symmetric, because if beta imaginary is under pretty symmetry with a minus sign, but here as well, and it's an even function. So you can check that the solutions, these fields are real, and now the singularity will remove the singularity, and now the solution becomes regular everywhere. And this is quite a nice feature. But then what will happen with energies? Well, now for you should not be a surprise. Also, this equation, the PD appear. This show you that there's an imbalance in this equation, and you can check that even despite the fields are now complex, the energies are real. Okay. So, well, this was not so exciting because we already know that this happens, but then the question is, what happened about the linear stability? So we take a static solution in spite of this, and we plug in into this scheme, and we arrive to this kind of potential. This is just, we have different solutions, this is just one of the potentials, which it looks like this. So the question is, may we now solve this problem and study what happened with the stability in this case? Well, and this is how also this spectral design and the idea that I showed you before is quite interesting, that it turns out that this kind of potential is related with this one, okay, because of this taboo or supersymmetric kind of transformation, but this nothing else than this. In other words, the one soliton kind of potential, if you rescale appropriately, and actually this is very related and almost the same that this kind of potential that I showed you also during the talk. And of course, this is related now, as we know this is related with the first system. So actually, for the linear perturbation of this soliton, we have all the explicit analytical solution in hand. So we solved completely the problem. And of course, if you take a look at this potential here, they display a singularity when x goes to this value, when it's real. But there is no singularity at all when this is symmetric. Okay? So we remove the singularity, which is we pay a price, the price to make it feel complex. But it has this proper this symmetry which ensures the reality of energy. So we don't care about that. So, and actually in this case, we found solutions that are linear stable perturbations among the different kind of solutions. But I will not show you the other details, but also we found new complex solutions. We also have real energies. But these, the associated potentials, I'm not going to show you, but they were not pretty symmetric. In those cases, there were not possibility at all to find linear perturbations. And this was quite nice for us, because this means that this pretty symmetry is not that an artifact to find real energies and ensure the reality of the spectrum, but also tells you about the physical condition of the theory and also to the stability, at least in linear perturbation. So, well, I can show you, if you want later, if you're interested, how there are new complex solutions that are not, they don't have this symmetry. I didn't put it here, did not show you many formulas, but this is quite nice in the sense of to understand that this symmetry means something else. This is what was done in the end of the last year. And well, just to end, just tell you that PD symmetry somehow is nice because regularize solutions, ensure reality of the energies, but also connects the idea of having linear stable perturbations also display the symmetry. I will show you now in the talk, but there also we found the cases when we find stability and instability for non-local solitons. Well, as I also said before, there is in the sense of gravity, there are many open problems related with all this non-local physics, but also the idea of having these integrability features into the gravity side. And of course, there are among these many open problems, this is something very nice that Claudio let me show me in few minutes ago about a work about Jessica regarding many features of a nice feature of gravitational solutions regarding stability, and in principle also, but those ones are related with the fields that are asymptotically flat in the sense of there is no cosmological constant. So in principle now all this kind of the idea of inspired in that can also apply here in the gravity side. So we are still investigating what the meaning of the solution, because actually we have so many problems that we try to solve it at the beginning. We are still working together with Marcela, Miguel, and Christiansen. We try to understand actually this Pandora box that we have. So I mean, we hope to have some insight to the gravitational solutions soon. But in principle, this open a lot of scenarios to be studied from the gravity side and regarding with the stability. So it's something that I want to comment. And well, that's all. Thank you very much.
Questions?
It's not a precise question. It's more like you mentioned Grosvenor at the beginning.
Mm-hmm.
Do you think something similar for the last model that you mentioned, the model, something similar could work for
Well, it's a good question, but first of all, related with Grosvenor, yeah, I think that's so. I took two kind of possible directions. So from one point of view, when you solve the Grosvenor problem in terms of the gap equation, when you took this approach, you arrived to the nonlinear Schrodinger problem. So in somehow, but the nonlinear Schrodinger problem is not so exciting in the sense that the fields are already complex. So you create some compound of fermions, which are these the bosonic kind of fields, and these are related that with some kind of condensate were related with the nonlinear Schrodinger. So it's not so the all the idea of PDE symmetry is already there in principle. So, but maybe which is
if you have the classical, I know only Grosvenor like as the classical nonlinear Dirac equation. You have solitons and it's completely open. I mean numerically it's saying that they are linearly stable. As far as I know, do something rigorous, it's completely open. So when I saw this last point, I was thinking.
Okay. This is well, and in this approach, actually, I don't know. I actually have no idea about stability of fermion fields. I don't know what happened. I mean, actually, it's a good question. I don't know what happened if you introduce in this way studying the linear stability. I don't know how this can be done, but for sure there are. This is what I am almost sure. There are solutions that among the Gros-Neveu family of solutions which are probably non-physical. And non-physical because they have divergent energy because they were considered to be real. And I am almost sure, but this is just a guess, that there is probably a way to regularize those solutions using this kind of approach. I cannot work on that, but I will not be surprised if someone says, oh, now we have this solution that can be regularized and can be applied for the Gros-Neveu. And actually, there are some solutions that I don't know. I was remembering how it is the status of the phase diagram of this problem, which is there are solutions which are naturally kind of divergent, but I know that they could be regularized, and actually they are not studies on the Gros-Neveu problem. So there is something quite direct to study in this point of view.
More questions? I have well, maybe the people in Zoom might. Do you have some question for the people in the Zoom meeting? Okay, so I have a first question. I know that if you consider, I don't remember exactly if it's anti or self-dual jump mills, Euclidean jump mills in 4 dimensions, you have something similar. Actually, you have this kind of zero curvature condition.
Yes.
So, how different is what you found in terms of?
Yeah, well, that's actually what this was in the one of the questions that we posed in the list of questions. This is something that we want to study. I mean, this is something that we for me, it's quite exciting to study that, but we have been trying to understand the first result first. I mean, because just to give us the idea, but going to your question, it is not clear for us how directly the three-dimensional gravity with negative cosmologic constants will be related with the self-dual Yang-Mills equation or the anti-self-dual. So we don't know. But this is in 3 plus 1. This is 2 plus 1. So the only guesses that we have, but this is just quite hand-waving because we want to put our hands on that, but we are like waiting a little bit. But one of the ideas would be with dimensional reduction of something. So introducing somehow some fields like in the spirit of Kaluza-Klein reduction. So there is a way to construct solutions in higher dimensions, for instance, with some gravity, so sorry, with the electromagnetic field. But then you make a dimensional reduction to that, and you can arrive to, for instance, a theory in a lower dimension, but with some extra fields or no. So that could be a way how to do it. But as I said, this is just very, very kind of naive answer that we don't know. But I mean, we know that now there is something quite interesting that and how it goes in one of the other directions, we don't know. I mean, and actually, from the this is also important for us that there is this. I don't know if you want, the Ward conjecture. The Ward conjecture says it's a conjecture, but that almost all integrable system comes from from reductions from the anti and self-dual Yang-Mills equations. So it's not only the AKNS system, the Novikov-Veselov, Davies-Stewardson. Many of the integral models can be obtained by reductions of these equations. So now, of course, we may ask what happened with this connection. So this is quite a good question, and we would like to go into that. Yeah.
When you consider, for instance, BTZ, that solution satisfy the boundary conditions that you?
Yes. Actually, this is quite interesting because, yes, of course. So I didn't want to go into the details of the gravity because I know how familiar are you with gravity, but so our conditions have as a particular case the Brown-Queneau conditions. The Brown-Queneau conditions in three-dimensional gravity, 2 plus 1, these are the ones that include the BTC black hole, the rotating BTC black hole, and some other solutions. So in our kind of simplest example, these are included. So we have inside the BTC black hole for sure. We have to understand some particularly how to obtain the bicertal reductions, but what I may say more precisely, when you choose our fields, which were dynamic and related with the integrability constant, and this means that they will satisfy any of the hierarchy, but actually the most simple one, like the chiral one, or for instance, the most, well, it's called the chiral equation, but also if you construct the KDB hierarchy, you realize that one of the first tenets of the hierarchy would be just first derivative in time plus first derivative in the spatial coordinate. And this is like the chiral one. So, and these ones are very related with the ones from BTC and Brown-Queneau. So, like the first term of the hierarchy is quite related with the BTC. So, it is included. It is included. We know that we more or less know. So, but this is just to comment that there are no. So the BTC black hole has very particular asymptotic behavior. So this is all about boundary conditions. So this solution, so So you may think, well, this is well studied, big steep black hole, and what is new? Well, we relax, these solutions will be relaxing in somehow. There are different ways to relax the boundary condition, but we will relax the boundary condition to satisfy some properties. So have some more generic functions, let's say, in the asymptotically, in the variables of time and the angle. The radial one, the asymptotically behavior in the radial one is almost exactly the same as the ones from the Brown node, which include the BT set. So what we are changing is the boundary conditions of the in terms of the angle and the time, which are the other two dimensions. So yeah, they are included, but also this is something that we are working now. How we understand these solutions, and also how we will recover the known ones in this approach.
I have a question related to the beginning part of it. So you mentioned the Darboux and Cron formulas for breaking symmetry, and maybe you said it before, but in the Bender-Bochum model where they had a complex pi x cube equation, was there any asymmetric breaking or?
Yes. Actually, I mean, I don't have here the plot, but it is very nice because one of the features of this model, which is nice, that they found the way to know exactly when a PTC is broken. So you find, if you put in internet Bender-Bochum 98, you will see immediately in Google like this image that show how the eigenvalues are real and how sometimes they become complex. And when they become complex, is exactly, this is related with the previous question, this is exactly happens when the wave function turns out to be not longer wave function of the eigen function of the PT operator. And this is when they found exactly where the PT symmetry is broken. And there are a lot of very interesting mathematical features regarding with the solution and the behavior of the Sturm-Liouville related problem, which they understood very well when and how this PT symmetry breaking appears and why. Yeah. So this is well, like this model is very well studied, and all these questions are quite interesting. But this have been studied from long time ago, so it's very nice.
No more questions? Okay. Now let's thank again Francis.